Let's think a bit about circles.
Well, let's think about the function little f of x equals the square root of 1 minus x squared.
What do we get if we graph that function?
Let me draw my coordinate axes, right? And I'm trying to graph the function y equals the square root of 1 minus x squared. And yeah, when I graph that, I get a semicircle.
Now we can compute this integral geometrically.
Well, let's think about the integral from 0 to 1 of the square root of 1 minus x squared dx, right? That just calculates the area inside this quarter circle. And what's that area? Well, the whole unit circle has area pi, so that quarter circle has area pi over 4. This is a geometric calculation of an integral. We can also look at the accumulation function. Well, here's a zoomed in copy of the graph of that semicircle, and here's 0 and here's t, so this area in here is exactly what the accumulation function calculates. It's the integral from 0 to t of the square root of 1 minus x squared, right, that's this graph, dx. Now my claim is that that accumulation function can be written like this, that integral is equal to t times the square root of 1 minus t squared all over 2 plus the arcsine of t over 2. We can work this out in a couple different ways. One way just involves differentiating. So I'm going to differentiate this side and get, I hope, the square root of 1 minus t squared. Right? That'll be a proof that an antiderivative of the square root of 1 minus x squared is this, with t's replaced with x's. Okay, so let's try it. Let's see if we can really pull that off. So let me just write down what I'm trying to show. I'm trying to differentiate this whole thing. So t times the square root of 1 minus t squared over 2 plus the arcsine of t over 2. And that's differentiating a sum, so I just have to differentiate this and add it to the derivative of this. And this first term is a product. It's the t times the square root of 1 minus t squared over 2. So I'm going to differentiate that product using the product rule. So it's the derivative of t, which is just 1, times the second thing, so the square root of 1 minus t squared over 2, plus the first thing, t, times the derivative of the second thing. All right, d dt, the square root of 1 minus t squared over 2. Okay, so that's the derivative of this first term, plus the derivative of arcsine t over 2. Well, the derivative of arcsine is 1 over the square root of 1 minus t squared, but then it's over 2, so I'll put a 2 there. Okay, so we're making some progress. I've still got to differentiate the square root of 1 minus t squared over 2, so well, let's just keep going. So this first term is looking really great. This is the square root of 1 minus t squared over 2, and of course I'm trying to get the square root of 1 minus t squared, so that's looking pretty good. Plus t times, now what's the derivative of this square root? Well, I'll put the over 2 here, so I just have to differentiate the square root of 1 minus t squared, and that's 1 over 2 times the square root of 1 minus t squared. And then it's times the derivative of the inside function, and the derivative of 1 minus t squared is minus 2t. All right, so that's the derivative of the square root of 1 minus t squared over 2. The over 2 is there, and that's the derivative of just the square root of 1 minus t squared. And I'll just add the derivative of arcsine t, 1 over 2 the square root of 1 minus t squared. Okay, now I can simplify this a bit. All right, what do I have here? Well, I've got a minus 2 here and a 2 there, so those will cancel. And what I'm going to be left with here is the square root of 1 minus t squared over 2 minus t squared over 2 times the square root of 1 minus t squared. That's this whole second term, plus 1 over 2 times the square root of 1 minus t squared. Now I'm going to combine these last two terms. Right? This is equal to what? Well, I'll put 1 minus t squared over this common denominator. So I've got this first term, the square root of 1 minus t squared over 2, plus 1 minus t squared over that common denominator, of 2 times the square root of 1 minus t squared. Now I've got something divided by the square root of the same thing, so I could replace this with, well, the first term, 1 minus t squared over 2 plus, this is something over the square root of the same thing, so the square root of 1 minus t squared over 2. Now I've got something over 2 plus something over 2. That's just the square root of 1 minus t squared. And indeed, we have made it to our goal. I started by wanting to differentiate this expression, and I ended up with the square root of 1 minus t squared.
The second method is a bit more geometric.
So I want to find geometrically the area in here. And I can break that region up by drawing this line so that I've got this circular sector and this triangle. Now what's the area of the triangle piece? Well, the height of that triangle is the square root of 1 minus t squared, right? The base is length t, and this hypotenuse is length 1. So by the Pythagorean theorem, the height of that triangle is the square root of 1 minus t squared. And that means the area of this triangle is its base t times its height, the square root of 1 minus t squared, divided by 2. Right, so that's the area of this triangle. What's the area of the circular sector? Well, I've got an angle here, which is theta, and by a bit of geometry, that angle is the same as that angle up there. This length here is t. All right, we're going to need that in a minute. So if I've got a circular sector with radius 1 and angle here theta, that area is theta over 2. But this length is t. So that means that I know a formula for theta in terms of t. Theta is arc sine t, right? Because, really, sine theta is t. And that means instead of writing theta over 2 for that area, I could write the area of that circular sector to be arc sine t over 2. So the total area here is arc sine t over 2 plus t times the square root of 1 minus t squared over 2. Right? And that's exactly what I'm claiming in the accumulation function. This term is calculating the area of that triangle, and this term is calculating the area of that circular sector.
Now what happens if we evaluate the accumulation function at 1?
So what I'd be calculating is the integral from 0 to 1 of the square root of 1 minus x squared dx. And that's what I get when I just plug in t equals 1 here. So 1 times the square root of 1 minus 1 squared over 2, 0, plus arc sine of 1 over 2. Well, that term is 0, and arc sine of 1 is pi over 2. So I've got pi over 2 over 2. That is just pi over 4, which is really the area of a quarter circle.
These pieces are coming together. We can compute the accumulation function just by pure geometry or some trigonometry. We can verify that its derivative really is the square root of 1 minus x squared, and then we can recover the area of a semicircle this way as well. No mathematical fact is an island.